ಅಪ್ಪ ಏನು ಅದರಾಗ ಆಗ್ಲಿಕ್ಕಿಲ್ಲ ಅಂತ ಹೇಳಿದ್ರು ಸರ್. ಅಲ್ಲ ಎಲ್ಲಿ ಕೆಳಗಡೆ ಈ ಕಾಲ ಬಂದಿದೆ. ಈಕ್ವಲ್ ಸಬ್ಜೆಕ್ಟ್ ಅಲ್ಲ ಅಲ್ಲಿ ತೆಗಿಬೇಕಾ ಇವಾಗ? ಗೊತ್ತಿಲ್ಲ, ಅರ್ಜೆಂಟ್ ಇದೆಯಾ? ಗೊತ್ತಿಲ್ಲ, ಅದಕ್ಕೆ ಅರ್ಜೆಂಟ್ ಎಂತ ಇದ್ರು ಸೆಕೆಂಡ್ ಫ್ಲೋರ್ ತಗೊಂಡೋಗಿ ಹಾ ಪರವಾಗಿಲ್ಲ. ನೀರು ಇಲ್ಲಿಗೆ ಇದೆಯಲ್ಲ, ಸದ್ಯಕ್ಕೆ ಇದೆಯಲ್ಲ, ಸದ್ಯಕ್ಕಿದ್ರೆ ಎಲ್ಲ ಸ್ಟೋರೇಜ್ ಎಲ್ಲ ಅಲ್ಲ, ಗೋಡೌನ್ ತರ ಅದೇ ಅದೇ ರೂಮ್ ಹಾ ಅಪ್ಪ ಇದೆ.
So I they about custom metrics and its identification. So if you were asking about this teacher identification, so we proceed to that because this will come about like custom metrics and its coordinates. So I'll quickly produce and then we move to the coordinates. So this is another matrix. This is defined in this way. If you have a simple graph, so then what you have to do, you just this way you can think that you put the diagonal elements as the degree of the vertices and the off diagonal elements like I just three or minus one. If I am clear adjacent, otherwise it's safe. Okay, so this way is defined. But then we can see that this is nothing but the degree matrix minus the adjacent element. So if I take degree matrix as the diagonal matrix, with vertex degree in the diagonal matrix, so that will be easy. Then you people know that LG is DG minus H. Okay, but it's originally defined in this way. And I think the definition in some other way also, that is that using the incidence matrix. So given the graph, we can define incidence matrix as a zero one matrix. But here I am taking a oriented graph. So if G is given, then you can orient it. So you will put division to each edge. That's known as oriented graph. So you take the graph C and then just make it oriented, so it's becoming a directed graph. And then QG, that is the incidence matrix, that is defined as, you can define in any, like EI is originate set that I'm putting 1, you can put minus 1 kilometer. So any one you can choose. And then if there is originating a that means EJ is the first vertex from where it's starting to reside. Then I'm putting the adjacent tree where there's 1. And if it terminates at I, I put minus here, otherwise 0. Okay. So this way, if we define here, I have one example. So the like I have oriented all like this. Now this matrix will be like you can see the rows are indexed by the vertices, and the columns will be indexed by the edges. Incidence value. Now for each edge, there are 2 edge vertices. And where it's starting, you will put 1. Where it's ending, you are going 1. Okay. So that way, if I look for 1 to that edge, that is E1, that is the first edge in the matrix. Okay. So you can see I have put at 1, I have put like first value that is corresponding to the edge 1 and the vertex 1. There I have put 1, and the vertex 2 where it is ending and minus. Okay, so this way the matrix can be obtained. Is it okay? So this matrix, if I take, I can express LG as Q cross. So that you can see in the example also, your Q was this, and then you can make Q transfer, you will get this. Okay, why you said it? While multiplying, you can observe why it's giving you. So for each edge, when I'm looking at, so Q is vertices and edges. Now when you multiply, so you are taking first vertex corresponding to that vector, and that will be multiplied with that. Okay. So then you will get like before vertex. How many edges it's incident with? That will come as the first matrix. That is your degree. Okay. Similarly, the others at this system, if there is some common vertex between them, if that vertex is and vertex for 2 edges, then that degree will come as minus 1, otherwise. So that way it will be like you can work with some example, you can observe this. And then I can say directly because it's reading as LG is some matrix transpose. So it's a positive symbol. Any matrix is a matrix, and I'm writing it as B to B now. So then A is positive symbol, right? That you know. So I try to write this Q into T transpose so that I can say directly it's positive symbol, but you can show also, I don't know. Okay. So it's written in this form, so directly we can say it's positive symbol, right? And LG, if I look at then the diagonal entries are all degrees. And if you look at off diagonal entries, those are basically what was in your adjacent symmetry, those are negative. Okay, so in the first row you can see the vertex has degree 2 And then in that row, octagonal entry, two octagonal into minus one are coming because which those is adjacent. So one is adjacent to two particular row. So if I add that, it's giving you this. So each row sum is 0. Because column sums are also 0 because it's a split thing. So each row sum is 0, then what I can say? So all one vector is one eigenvector corresponding to the 0 eigenvector. So it's a positive segment matrix and 0 is one eigenvector. So you can look for how many zeros you will get, but one 0 is there. Corresponding vector is all one vector. Okay. So now I can say that because all one vector is one eigenvector, and you can get the orthogonal set of eigenvectors because it's a symmetric matrix. So all the other eigenvectors they are orthogonal to all one vector. Okay. So if that happens, that means if I take any other vector, x1 to xn, which is one eigenvector for LG, then this is orthogonal to all one vector. So what I can say? The summation of xr that will be 0, right? So if I am choosing any other vector, it has some positive and some negative entries. Okay. All cannot be there because it's eigenvector. So certain positive entries will be there, negative entries will be there, and some negative entries. That happens for any other eigenvector. Okay. Now, as I told, like we can also decide how many zeros are there in the eigenvalue. So for that, I'll show that if you are taking D as a connected graph, then the rate of the incidence matrix using that is n minus 1. Okay. So incidence matrix you remember 1 0 minus 1 matrix, and that is rank n minus 1 if the graph is connected. How to prove it? We look for because QG is not a square matrix. It's if you have n eigenvalue, then n rows of the graph is of order n, and let's say n edges are there, then the matrix will be n cross n, right? So it's not a square matrix, it can be rectangular. So what I'll do, I'll take a vector x, okay, and I'm taking like left null space gap. Whatever vectors is a line in the left null space. So I just took one vector x and multiplied with using, and I'll make it 0. So how many such vectors are there, independent vectors? That will decide polynomial, right? So if you take a vector x and just multiply with using, you can observe as I have already written here for that example. So x transpose using, okay. Now you can observe because every in QC, each column contains one minus 1. Right? So when I multiply, so corresponding to like 1 for it, like that is the edge. So the first entry is 1 and then minus 1 in that one. That will be multiplied in the vector. So you will get x1 minus x. Okay. Similarly, you are getting the second one is x1 minus x. And that is the 1 free edge space. That's why x1 minus x. Similarly, the other edges, according to your edges, those means those columns are there. So corresponding to that, you will get some xi minus 60 if ij is for the edge. Okay. So you will get those terms. Now that if I make equal to 0, then what I will get? X1 equal to x2, x1 equal to x3. Like this, where there is one edge, I'll get those 2 and 3. Okay. And the graph is connected. So from every vertex I'll start, I have one edge, is the next one. So those 2 entries will be equal. Then I'll go for another edge. 2 entries are also equal. So all will become equal. the graph is connected from any vertex and that I can reach to any other vertex, right? So that way I can say that x1 is equal to x2, is equal to x3, equal to x1. So when I took one vector in the left null space, I observed that it's nothing but all one space. All the entries are same, so it's all one vector I think. So that is the only vector that is lying in the north. Okay. So what will happen for the ring? The matrix is size m cross n. So now I can say that ring कितना होना चाहिए? लिखा हुआ. So in a null space is one dimensional. So rank of Q's will be at least. So now the other thing is how many columns rows you have, n rows. Okay. And if you add some columns, like each column substituted, that is equal to 0. So your rows are dependent on you. Okay. So your rank can be n minus. So together you make 6, then rank will take that equal to. Rank cannot be n because the rows are dependent on you. So one rank at least is. And also null space contains a form one vector. One. Okay. So rank will be exactly n minus 1. Then what do you have defined? Like if I take a connected graph, it is n minus 1. Now if the graph is disconnected. Okay, so range is n minus 1 for Q is equal to 0. Now if the graph is disconnected, so then range will be, if k components are there, range will be n minus 1. And that will be easy. Because if the graph is disconnected, we will express your Q using clockwise corresponding place. So then your range is sum of the range. Okay, and for each one, it will be this one. So totally you will get your n minus. Okay. Now you have defined that LG is nothing but Q into Q transpose. And Q current from that. So L current है connected graph on the C. N minus 1 that you can call. Now another thing here is using is totally unimodular. Totally unimodular means if you take any space of matrix and take the determinant, that will be either 1 or minus 1 or 3. Okay. So can you approve it? So in induction then what do you do? Any 1 plus 1 submatrix you can look for, that is the basic state. And because the entries are 1, 0, minus 1, so any 1 plus 1 submatrix you write it, that will be 1, 0, or 1. That I know. Okay, so if I'm using the first step is algorithm. Okay, is the then you assume first step k or k minus 1 and then go for k. Okay, so you take a submatrix of size k and assume for k minus 1 and 2. Okay, now then choosing the submatrix. So it's containing 0, 1 and minus 1 entries, but it's a square matrix. Okay, it may have been that you have like how the entries are unique that can happen. You may get a 0 or 0 column. In that case, it will give you 0. Okay. And if you get one matrix like some one is there, another minus one is there. Okay. And like if every well, if you can get this and waiting here. So each column of B has a 1 and a minus 1. Okay. Like in your, I can take for example. So if I choose the submatrix and let's say I have like this. Okay, these came off. So where you can see every column has a 1 and minus. That's why I can also even putting one submatrix. So if each column in the submatrix has a 1 and minus 1, then you know that rows will depend. Because if I take the column from 0, 0, okay, so rows will depend in that. So if each column contains 1 plus 1 and minus 1 in the submatrix, then the determinant will be 0. And if there is a 0 row or 0 column, then also the determinant will be 0. So the third case is it may happen that there is some column that contains exactly 1, 1 or minus. Okay. If there is exactly 1, 1, yeah, let's set this aside. Okay, now I will calculate the determinant. So what I do, because exactly 1, 1 is there, that may happen here or here, I'll expand the determinant corresponding to that. Okay. So basically the determinant will be this determinant. And here we use a because that size is less. Okay, so determinant will be 1 into determinant of this. This determinant, if I am estimating 1 or minus 1 or 0, then I will get the denominator for you. Okay, so here you are using junction. It's correct. For a C, if you will choose any submatrix of QG of order n minus 1, 3 में n minus 1 is the set. Okay, so when I'm taking one 3, there are n minus 1 column. Okay. Like this. What the result is saying, if you choose any submatrix of order n minus 1, that means you need one row. Okay, then it becomes non-zero. That's true. So you red you showed now. Anyway, consider any submatrix, okay, of QZ that is formed by like I am taking X in the solid that is formed using at n minus 1 load. Okay, n minus 1 order of submatrix I have taken. So what I do, I just take this submatrix. This is n minus 1 cross n minus 1. So last one I leave. Okay. Now if I look at like I just add all the rows. Okay. But I can see that if I add all the rows of this if you see all the columns, if I'm adding all the entries, I was getting 0, 0. Because each column contains 1, 1, minus. So if I add all these rows and minus 1 rows, whatever it will come, there will be negative of this row. Okay. So if we add all this, like row 1 to row minus 1, that is nothing but negative of row n. Okay. This you can also so if I take like I took this one, this I am taking x. Now if I consider another, then I am taking like one. I'll leave another one this one. Okay, I'll take 1, 2, 2, n. Okay, that matrix is y. So this matrix if I look for this, this, and this, and this. This is my logic. Yeah. So what we observe is if I take the like sum of these rows, I'm getting these two. Negative of these two. Okay. So what I can say that any like n minus 1 rows if I'm choosing. Okay. Like I'll choose 1, 2 up to n minus 1 and n. Okay. Then also whatever the matrix will come out, the denominator of that matrix will be same as the denominator of the second matrix. So which row you are leaving, and it's nothing but if you add all the other rows, that row is full. Okay, so within your denominator, so basically if I take any other, like any row as leaving, okay, whatever the denominator is coming, that is same for every row. So if your x is this matrix and y is let's say leaving this one, denominator of x will be same as denominator of y. Because column sums are 0. Hence, you are adding all the rows, then it's coming 0. So one row is negative of the sum of the other rows. Okay. So if I leave one row, okay, then denominator will remain. So denominator of x and denominator of y both are same. And that happens for any zero sum row or zero sum column like this. Okay, if you make the like if you have all the row sums are also 0, then also this thing happens. Okay. So if the denominator of x are making 0, the denominator of y also will be 0. Similarly, any row you have in, the denominator is 10. So one of them if I am making 0, all others will be 0. Okay. Then your rate will decrease. Or Q is Q. And that's not Q. Okay. So you cannot take J. The range of Q is and minus. If all the sum matrices of rank means of n minus 1 size is giving you the dominant 0, then rank of Q will be right. So that should not be rank of Q will have obtained as n minus 1. Okay. So you cannot make the denominator 0, so that will be not similar. So any n minus 1 plus n minus 1 size sum matrix equal to 8. When you are taking then they will be non-same. So then we have these properties of the Laplace matrix. That one thing we observe is G will be symmetric if the matrix if the graph is simple and it's a positive sum matrix. And if G has K connected components, it's disconnected and K connected components, rank will be n minus n. So you have 0 identity replicating number. And third thing is you can also express your H transpose LGX as this in this form. That will give through one example. I can do like later also I will get. But that way, if third one can be true, you can from there also you can say that the matrix is positive symmetry. Because you are expressing in squares. Okay, so that way also it's good. So you can always write like if I'm taking X transpose LCX, then it will be the sum of xi minus xk, where I is the edge. So that sounds clear. And then the row sums, column sums, there is 0. And co-factors of any two elements of LCL 1. Those I'll go. So these things will happen. So first one is already clear to you. Second one is clear because we find in terms of using. Third one you can see in the example. If I'm taking X transpose LCX, okay. So it can observe if you just directly multiply also. You will get that your degree will be multiplied like when just see that the matrix into the right side take over and multiply. Okay. So you have to increase one more increase the degree. And the second two entries are where one is adjacent. Okay. So one more entry is degree, that degree will be multiplied with h1. That will give your half expression and calculating. So 2 will be multiplied with h1. And then minus 1 will be multiplied with h2. And then remember that 2 is adjacent to 1. And similarly, minus 1 will be multiplied with x3, where 3 is adjacent to 1. So what we get, you will get a term as 2x1, where 2 is nothing but a degree. And minus 1 is getting multiplied with the coefficients, which vertices are adjacent to 1. Okay, so that expression will come. Similarly for the others. Now again you will multiply the zero. Okay, it transpose. So what we get is again 2h1 square. So whatever degree was there of h1, we will get a term to h1 square. Okay, and the next term was h2, x3. Those were the vertices which were adjacent to 1. Now with those we will multiply h1. So the terms will come as h1, h2. X1, x3, and remember that 1 is adjacent to x2, 2 and 3. Then you are getting those two terms. Similarly, in the other group, like you are getting like in the figure, minus x1, 2x2, minus x. 2x2 came because the degree of 2 is 2. And then 2 was adjacent to vertex 1 and vertex 3. So these two came. Again, this part will be multiplied with x2. So that will give you 2x2 square. So 2 is the degree for x2 vertex. And then it's adjacent to with h1 and x3. Then you are getting minus x1 x2 minus x2 x. So that way the terms are complete. Okay. So now you can express this because x1 square and this. So you can write it in this simple form. So I am taking together so that I can get square square. So how many like for vertex 1 to h1 square came, but vertex 1 was adjacent to 2 vertices. So that way I will take so that I can write x1 minus x2 whole square, h1 minus x3 whole square. So you can write it as well. Okay. So then your total sum is expressed as some squares sum. Okay, so that will happen. So here I just told you to show the example, and that's the thing it happens. Okay, there is no other proof idea. This way, it's an observation, and then this. And next thing I told, the co-factors of any two elements are equal. Okay. So that will improve. Row sums and column sums of LC are 0. That we know. Now let us take the ith co-vector. Okay. So ith some matrix I am taking, that is Lij. So I am taking I row and Z column. That is LI okay. We look for the covector corresponding to I Z. So that will be minus to the power I plus Z into the determinant of this matrix. Li. Okay. Li is the symmetric. So then by deleting the I4 Z column. Okay. We look for the ith covector. Okay. So this is for any ith. So now what we know is SGX row sum follows some 0. So actually it will be a equivalent looking for the determinant of N11. Okay. N11 means I'll so this is the original matrix. Okay. Now we are looking for the covector that is obtained by deleting the hash row and hash column. So that will be if I look for that one, so that will be noted as N11. N11 is you are deleting this one and this two. Okay. And we are going to calculate minus 1 to the power 1 plus 1 determinant of this. Okay. So now this is our matrix. Observe that the row sums are 0 for the Laplace and column sums are 0. Okay. So when I compute the determinant of this, like earlier also I did the same thing. So on this determinant I am going to compute. I can add all the rows, means all the columns to this hash row. Determinant never changes. Okay. So if I add all the columns to the or all the rows, you can make any one. So if I just take all the columns and add to this column. Okay. So here, so your expression hash column will be these ones, and the other columns will remain same and two. So the first column I just added all the columns to this, and the others separately. Okay. So this is your. But you knew that the there was some in the Laplace that was here. Okay. So this total sum plus N21 that makes it. Okay. So this total sum is nothing but this is minus N21. Similarly, here your N32. This sum is negative of N31. Right? So I can put this as negative of N3. Similarly, this sum is nothing but negative of Ln1. Okay. So I'll put this as negative of Ln2. So the determinant of this matrix is nothing but now the determinant of this matrix. Here we have it. Okay. Then this is if I take out minus 1. This matrix is this matrix as per our notation. You can say your first row is needed and this one is equal. That is the second column. The first column is there. 1, 2 is deleted, second column is deleted. So this is -1 into determinant of n. Okay, and this -1 came because this is 1 plus. Okay. Okay. So what we would show that the cofactor of 1 is same as cofactor of 1. Okay, but what I did is I took all the columns and added to the second one. That's why the second one. Yeah. But I can add to any other column. Okay, so I can show that this is same as -1 to the power 1 plus j. Any column I could have that percent. Okay, so all these cofactors are equal. Instead of okay, we did by adding the columns, we could have done adding the rows also. Okay, that way I could have done like all the rows if I had internet before. Okay, so I would have get this one, that is -1 to the power 1 plus 2. I would have given this. If second row is higher. Okay. Similarly, we can prove that it will be same as in place of 2, I could have done for any row. Okay. So this would be okay. So I started with N11 and then I could prove that in place of 1 I can say I in row case or in column case. Okay. So every cofactor of this form or this form they are equal to this. Okay. Now I could have started with anyone. I started with 1, but I could have started with I. And I can show everyone is. That difference is automatically coming because you are taking 1. That is okay. That's coming. So you observe that L11 here sign was plus 1. Okay. But when I did this one operation, so I got 1 point. That is coming like that. Okay. So all the cofactors they will be equal. Now this is about matrix, Laplacian matrix and its properties. So now why this will be used in your identity here. So now if I look at the spectrum of the matrix, so already you observe that if the graph is connected, there is 1 0 I will below, and others will be non-negative, means positive. Okay, because it's a positive solution. So what we can prove that the graph is connected if and only the second smallest eigenvalue is 0 than 0, and that already we have proved. Okay. So this eigenvalue is known as algebraic connectivity because it decides basically the connectivity of the graph. And this like if you look at eigenvalue they decide also how the graph is connected. Okay. Like for example, if I take the complete graph, all the eigenvalues with the largest one. So the smallest one is 0, and then all the other eigenvalues are equal to n. And you can also take any highly connected main system of connected graph. So some of the eigenvalues are like value the second smallest, and the other eigenvalues they tell you about how much connected the graph is. Okay, so it's the second smallest eigenvalue is large. In this case, it's n. Then it's fully connected. In path case, you can see that it will be less than 1. Okay, and the smallest one. So that's less connected, we can say. So the matrix theorem can come Kelly theorem. Kelly theorem is saying that if you are taking like n vertices, then there are exactly n to the power n minus 2 is being labeled trees with n vertices. Okay, that means it's saying that if you take the complete graph, in the complete graph there are, like if you label the vertices, okay, then in the complete graph there are exactly n to the power n minus 2 spanning trees. Okay, so here I shall give the example. So spanning tree, means it will take all the vertices. Okay, spanning means all the vertices should be there in the subgraph and it's a tree. So that's spanning tree. Here labeling method, like if I take one this 1, 2, 3. By the spanning tree means I'll take a tree inside this. So I can delete any edge because here 3 edges, 3 vertices. Any edge deletion will give you a tree. Okay. So I can have this 1, 2. This is the spanning tree. Similarly, if I take this one, I will this one and like this. This is 1, 2. This is also a spanning tree. But for us, we say that both are paths according. Okay, both are same. But actually, the only we are doing here considering labeling. Okay, so this path is different from this path. The numbers, if you see, is just take out the numbers, both are same class. But when I put the number, the chain vertices have certain importance. Okay, so the practical purpose, each vertex is representing something, so they are different. Okay, so then this spanning case is counted as different from this. Similarly, I can have another also. Here the vertex 2 has degree 2, others have degree 1. Here vertex 3 has degree 2, others have degree 1. Here vertex 1 has degree. So all three are different if we consider the vertices different. Okay. So now the question is how many spanning trees are there? Like, or this is the graph is the combination of K. Okay. For K3, is there anyone else? Only 3 because any else to take it, you are taking 1. These are 3 ones. So there is 3 spanning. Now if I go for K4, how many spanning trees? I have written the formula so you can happen. So it's for complete graph. Okay, this formula is for complete graph. But if I take any graph, this is getting theorem is for complete graph because it's looking at all the spanning trees with 10 vertices. Okay, but one can think of it, you start with any graph and then look for all these spanning trees. Even this Kelly theorem look is not easy. So you have to there are many groups. So I can put it anywhere, but there are which group you were using that is again Kelly. But anyway, this is really only for how many spanning trees are there complete. But the question can be asked how many spanning trees are there for any graph. That's the features matrix here that tells you the cofactor of any element of matrix is same as the number of spanning. So we proved that all the cofactors are equal. So now that any cofactor, whatever the value will come, that we don't have. So that's the number of spanning trees. Okay, and why the formula is n to the power n minus 2? Because I can get, if you take a co-factor of the complete graph, then that will give you a division. So we can simplify actually, we don't calculate the co-factor. If we take a co-factor, what would be the value? Co-factor means you are considering a submatrix, which is size n minus 1 cross n minus 1. You can take a benchmark submatrix also, that has also the same denominator. All the co-factors are same. What it does is, so you already know how to compute the, like given any matrix, how to compute the coefficient that you know, right? So here your matrix is n, but for any matrix you can do this. If I want to calculate the coefficient of characteristic column, you know that first one you calculate taking the sum of all 1 plus 1 principal matrix. Second coefficient, like which is x to the power n minus 2 coefficient. That is, you add all the 2 rows to principal matrix. Okay, like this it continues. I look for all n minus 1 cross n minus 1 of matrices. Okay, and principals of matrices and add them. What it will give? Coefficient of what? X. And what it returns? Some percent of. So what it is? That coefficient, but that coefficient, what it means for
All possible n minus 1 significant minus 1 principal minus.
minus, but what does sum mean?
Product of the values taken n minus 1.
N minus 1 times all possible n minus 1. So if I take click n11, this determinant minus 1 to be 1 plus 1, that will be 1, so that I am like. So this plus like this. Okay, these all if I add, let me know that that is here like this is one side, here all the possible n minus 1 products are here. So this is lambda 1, lambda 2, lambda n minus 1 plus lambda 1, lambda 2. 1 I leave, so lambda n minus 2 to this, like this. And we want to collect this off. These all the possible products we get, add them, there is some else. Okay, all principal methods of science. And here all are equal that you know. So this may be something, so that is n times L1 will be this one. It will all are equal. And this side, if you look at, what do you get? So your lambda 1 is 0, right? So whenever lambda 1 will come, everywhere it will come except this. So all these terms are 0, except this one. This is lambda 2 to lambda. So 1 and will be 0. So in all terms lambda one we are pairing except in one. Okay. So except that all everywhere is same. So what you got is the coefficient n11 is lambda 2 lambda divided by n. Okay. So we take the non-zero eigenvalues. If the graph is connected, then only we get spanning tree. If it is connected, then spanning tree is not there, so it will give you 0. Lambda 2 give you 0. If the graph is connected, then lambda 2 lambda is there positive numbers. So this multiply divided by n will give exactly the number of spans. And the Kelly theorem then comes with the corollary. Because for the complete graph, you know the eigenvalues. So that's 0 and n. Now if I take n multiplied to the n minus 20 number, so I divide n by n. So n divide 1. Okay. So here I am making the proof, so you can go through. Like for this one, if I calculate the eigenvalues, eigenvalues are 0 to 4, 4. Okay. So I know that 8 number of spanning trees will be. Okay, but if I see like this is like one cycle and then one extra, you can think, or a complete graph A4, deleted one edge. Okay, but numbering can make us. So if you see the spanning trees, so I have to delete 2 edges, right? So 5 vertices and 5 edges, and 4 vertices and 5 edges are there. Make it 3, I have to delete 2 edges. So sequentially I have done, it is this is one and then the other one. So I deleted the top edges and then side edges. These two are around. These are. So R6 are all partial. And then 2 star. This theorem has been generalized also. Artistic theorem. And reference the coefficients of each term. Like in the adjacency case, you had calculated like C1 is 0 and then C2 is the number of edges with a negative sign. C3 was representing number of triangles. Right? So here I am asking what is C n minus 1. Okay. C n minus 1 given as number of spanning trees divided by C. Okay. So all the these coefficients can also be computed. This is the generalization of matrix theorem. So like adjacency case, all the coefficients we know how to calculate. Here also all the coefficients can be calculated. Adjacency case you were calculating, right? Using linear subgraph. You know already. Like last coefficient is the dominant. And C2 was representing the number of edges. C3 was giving number of triangles with something like that. So here also like column less than. One can compute looking at the graph. So you have to take the spanning trees of certain size and then here. So now in Laplacian case there is an important problem that is tree of, and to understand it it's very simple. But to work on it's not easy. So that's the brown one. Okay, so before going to this, like you need to know what are good terms. So your eigenvalues here, I just tell the ordering lambda 1 is bigger. He is obtained from G. by identifying all vertices of S. So you are taking a subset S. Okay. All the vertices you just take H1 vertex. So basically you are taking all the edges adjacently, means in between them and make one vertex. Okay, then you get a graph. Like in this graph, I get these two as S. 1 and 3 are in S. Okay. What my graph would be, GS is 2 and 3 and 1, 3 and 3, whatever edges are there, those all like they can just. So that will be like. So it's identified all the vertices which are there. And that will give you all the edges. Okay, so we go to this conjecture, graph conjecture. Before that, I am defining this. While defining, I just change the ordering because to write it will be easy. So the lambda one I am now taking a bigger one. Okay, the largest I can do lambda and latest one. So this way I have changed the ordering. Okay, so the SKG can be defined as. Otherwise, you have to write 1 to. I started I equal to 1 to k. So that's why I wrote it. So SKG is defined in this way that you take the k largest eigenvalues and add them. Okay. So sum of k largest eigenvalues, that is SKG. Just to write nicely, I will change the order. So that from the beginning like that. So S1G is lambda 1. S2G is lambda 1 plus lambda 2. Okay. Lambda 1 is the largest, lambda 2 is the second largest. Like this is one. So sum of the largest k I, that is SH. Now degree sequence, you know the degree sequence also I can write. You take all the degrees and write them in this way. Ordering. So A1 is the bigger one. B2. So all the degrees you can take and you can make that's known as the degree sequence. Okay. Now the conjugates of the degrees that can be defined in this way. The T1 star is how many degrees which are greater than equal to 4 or like 1. Okay. So if you take a graph, okay, this is the graph. Here your degree sequence is D1 is 2 and this is 2 and okay. Now D1 star is how many degrees are greater than equal to 1. That will be similarly D2 star, that is how many degrees to the greater than equal to D3 star, how many degrees are greater than equal to 3. So that's it. I can continue D4 star. It will continue, but after certain time it becomes 0 square. Okay. This is known as like if I take all these conjugates, I can form this system. Okay, up to finite term, let's give some integers, and after that it becomes 0. So it's basically you can go up to on this, so that will be a finite sequence. But I can add some more. Okay, zeros. So that is known as a conjugate sequence. So here in this example of you can say 30 degrees are 2, 3 and 1. You cannot have them all. Okay. But degree conjugate degrees will be D1 star is how many degrees are greater than equal to 1. And that's all 4 vertices. Okay, so 4. And then DQ star will be how many partitions of degrees greater than equal to? That is 3. Okay. Similarly, you can compute. So D3 star will be 1 here and D4 star is 0. Then. So what was the conjecture posed by Roll and Maris? They hold the conjecture that SKC, that is the sum of k largest eigenvalues, that will be less than equal to the sum of k conjugate b. Okay. So that was the Roll-Maris conjecture. Ordering is kept in that way, so it will make otherwise that way. So SKZ is means lambda 1 plus lambda 2 to lambda k defined. That will be less than equal to T1 star plus T2 star. Okay. And this conjecture has been already proved by so it's known as Roll-Maris by okay, that was proved in 2011. Then another conjecture that was posed, that is the Brahma conjecture, that I have written already. Some of the k eigenvalues, largest eigenvalue, that will be less than equal to the number of edges plus k plus 1 zero. Okay, and this conjecture is long. So the developments are done in this way. Like if you see lambda 1, the largest eigenvalue is always less than equal to n. Okay, and you want to prove that it's less than equal to like sum of the k eigenvalues, that is less than equal to number of edges plus k plus 1 zero. But if I take lambda 1 is less than equal to n. So for k equal to 1, okay, then the statement is what? If k equal to 1, then S1 that is lambda 1. That should be less than equal to the number of edges plus k is 1. So that is plus 1. Okay, and that will happen because number of edges will be n minus 1 is the least time constant that is for k. Otherwise, number of edges is greater than equal to n. We are adding 1, so that is t. So for k equal to 1, that means the conjecture is true. Similarly, if you take k equal to n or k equal to n minus 1, k equal to n means you are adding all the eigenvalues, and k equal to n minus 1 is sum because half eigenvalue is it. Okay, sum is sum. Now we have to show that is less than equal to number of edges plus NC2, and that's because sum of all eigenvalues is same as sum of all degrees, and that's 2 times the number of edges. Or you are adding number of edges plus NC2, so that will be a real quantity then 2 times. So for n equal to k equal to n and n minus 1, your conjecture is k equal to 2, the conjecture also holds, that was very much. And this chain measurement is important because it's saying that if the conjecture holds for all graphs with k equal to p and p lies between 1 to n minus 1 value, then the conjecture will hold for any k that is n minus p minus. Okay, and this result that improved to prove that then for k equal to n minus 2 the conjecture is true, n minus 3 the conjecture. And several developments are done, like for trees and threshold graph, the conjecture holds, that is proved by Hemos. And for unicyclic graphs, bicyclic graphs, that is also what the conjecture holds. So that's proved by Hu and Zhou. regular graphs and split graph. For them also the quality of work. So that is 2 by 1. So you can look for the conjecture. In the conjecture appears in the book by Brown. The developments already I have given the suggestion. Many people are working. Brown conjecture also holds like if you take corner two graphs, if both the graphs are satisfying Brown conjecture, the corner will satisfy. Equality. Equality. Yeah. Equal. And that is also there. You can think what happens in computer. What happens in computer? If I take a cell, what do you get? And what do you get in S and minus? One of them is equal to 0. Even for quiz classes is done, but it's very near to the equality. That's why it's very difficult to actually it's becoming that and there it's difficult. It's power is the type of alternative. Okay, so for the like as I was saying, if two graphs are satisfying this Brown conjecture we are assuming, we can show that like their corner also satisfies, their Cartesian product also satisfies. These two are both possible. But that way also one can handle. But the question is for everything. For certain classes, they told like regular classes, then it's proved to be. But for all graphs, it's not. Another problem is we understand or at least say so which graphs are determined by spectrum. So whether there is like if you know that the complete graph has the ideal values for the Laplacian, it's 0 and all of them. So whether there is another graph with the same spectrum or complete graph is the only graph with that spectrum. Okay. So if there is no other graph with that spectrum, then we'll say that the complete graph is determined by the spectrum. So with that spectrum, we have only one graph. Okay. But if not, then you have another graph with the same spectrum. Then these two graphs are known as co-spectral. Two graphs having the same spectrum are known as co-spectral. So when you have a co-spectral pair, getting it is sometimes like easy. So you constructed another graph and that has the same spectrum. But when the graph is determined by spectrum, to prove that it's determined by spectrum, that means there is no other graph with the same spectrum. That's a difficult problem. Okay. So few graphs are determined by the spectrum, and therefore complete graph is determined by the spectrum. Similarly, like paths I get they determined by the spectrum corresponding to what exists. Okay. So I'll tell you these are two like the smallest non-Iwsmga graphs with the same spectrum. So the smallest, I mean, 5 vertices. Before, like if you take 4 vertices, 3 vertices, all are determined by zero. Okay, so this is the first 4 spectral pair. You can see one is disconnected, one is connected. That way. But connected pairs are also there. That's way. So how do you equal the problem of determining like when the graph is determined? To prove it's determined by the spectrum is not easy. Like for path case, I'd say it's proved. So path is determined by the existence spectrum. That will prove. So we have discussed yesterday the eigenvalues are 2 cos pi and then it goes, right? So that I told is strictly less than 2. Okay. So that eigenvalues for path, they are strictly less than. Other they only used here. So if you have not verified, then also like remember the restriction less than 2. So now I look at all the eigenvalues and the spectral radius is strictly less than 2. Okay. So then if I think of any graph with the same spectrum, okay. So I know that the spectral radius must be less than because it will take the same eigenvalue. So let us take a graph G and let us think that it is co-spectral with here. If I can show that G is isomorphic to Pn, then I'm done. I'll say that Pn is the only graph with this spectrum. Okay. So I took any graph G. And my information is it has this vector. Okay. So from the spectrum we can get how many edges are there. Okay. How many like edges and how many vertices. If n eigenvalues, so I can say that n vertices should be there. So G must have n vertices. I cannot take less vertices or more vertices. Okay, I'm looking for same spectrum. So G must have n vertices. Okay. Similarly, since spectrum of Pn is same as this, so I know that the sum of the lambda 1 square, lambda 2 square, lambda n square, that gives me 2 times the number of edges, right? So that should be also same for the other graph. So the other graph should have n-1 edges because Pn has n-1 edges. Okay. So that is coming from trace of a square. So the number of vertices, number of edges should be 7. Okay. But then the graph may be disconnected. If the graph is connected, I can say that n-1 is edges, so it must be 3. Okay. But it may be disconnected. Okay. So we look for whether there is a cycle. But if there is a cycle in the graph, then your spectral radius will be 2. Okay. But spectral radius should be less than. So there is no cycle in the graph. And then you have like your graph is a tree. Because n vertices n-1 exists and there is no cycle. So it will make it connect. So it's a tree. Okay. Now it's a tree, you cannot conclude that it's a path, right? So if it's a tree, I have to see that degree 2 vertices will be exactly n-2 and there are 2 pendant, then only it will be a path. Okay. So we look for then like high degree vertices. Okay. So if there is a S5 in the graph, that means there is a vertex with degree at least 4. Okay. Then S5 has the spectral radius 2. Because S5 is a complete bipartite graph. Here 4 and here 1. So the root over of 4, so that is 2. So S5 has spectral radius 2. Okay. So then by introducing your whatever tree that has spectral radius 4. So that cannot happen. So S5 cannot be a use of graph or the tree. So there is no vertex of degree 4. Okay. So degree 4 vertex will not be there. Now we have the chance that degree 3 vertices are there, degree 2 vertices are there. Okay. Now if there were 2 degree 3 vertices, then the situation will be like this. There are other parts and sitting degree 3. They are connected by a path. So this will be a subgraph in that. Okay. So and assuming let's say there are 2 degree 3 vertices. Okay. So then this graph is a subgraph of that. In between your length may be 1. This. But this type of situation would be there because you are taking 2 degree 3 vertices. In that case, you can see that if such graph is there or such tree is there, this tree has to each one argument. And I put the corresponding vector actually. If you take the vector 1, 1 and 2, 2 everywhere in the middle, and then 1, 1. This vector will be eigenvector for 2. Eigenvalue 2. So 2 is eigenvalue for this. Okay, if 2 is eigenvalue for this, then the speculative of the tree is bigger than or equal to 2. So that 2 should not have. So 2 degree 3 vertices we should not have. Okay. As the degree 4 vertices are not there, degree 3 vertices is there, they cannot be more than 1. Okay. So 2 cannot be there. So then we are thinking that it has, let's say, 1 degree 3 vertex and other side degree 2. Okay. So 1 degree 3 vertex means then the value for other parts. So what we know is trace of a to the power I, that is same as trace of the new graph what we are making. See, so a of Pn, if I take the trace of any power, that is same as trace of a of, because there is something as lambda 1. Okay, this a to the power I. It's trace and saying. That means if I take it, it will be lambda 1 to the power I. So when some graph is posed between G, this would have this set. So trace of this is an trace of A of P then. So this will be same. So then close to one if count, okay, of any size. That should be same for a foot. So we look for like let's say you have a like a vertex of degree 3, okay, and in path you don't have a vertex of degree. So, but both are co-spectral. So if I want to count the closed ones of any size from I to I and add them, that will give this stress, and those are segmental. Okay. So what we do, we count the closed ones of length 4. Okay. So one graph in this situation that you have a degree 3 vertex. So I am considering that part only. Okay. The other is part 1. The part is it is like this. So I'm considering only 4 vertices so that you can realize what is happening. Okay, so we are going to count the length for paths or walks from a vertex to itself so that I can compute the trace, the diagonal length. Okay. So of a to the power 4. This I'm looking for. Okay. The walks length from 4 from this vertex. Okay. Now if you compute, if your path is there, okay, when you are looking for length for what, how it will be computed? So you start with one vertex. Okay, and then you can go to another one is that we use one and come back again more again come. Okay, so each vertex which is adjacent to it, you can do. Okay, so like one from one, if I want to start in a path, 1 to 2 I go and then I come back and then again 2 and then come back. That will give a length more long. Or I can do I go to 1 to 2 then 2 to 3 and then I come back. That will also give you. Okay, so each edge will give me 1 and each like each part of order 2 that will give also 1 for 1, 1 second. Go from 1 to 2, 3 and 3 go back. Okay, that will be a for 1. And then from 3 to 3 I can get similar. Okay, 3 to 2, 2 to 1 and then go back. That will give 1. And then from 2 to like I can use 2 to 3, 3 to back and like this. And I can go from 2 to 1 and then go back like this. So if I take a huge part of size 3, when 3 vertices, how many will be created? 4, right? In that. Or you can keep like this, you are making all edges this way. So if I count here and here, in part, how many 4 ones are there? How many vertices to itself? It is come. I have taken 3 for 1. So from 1 I go to 3 and come back that way 1. And then from 2, I can go to 1, come back like this, I can go to 3, come back like this. So that will get 2, so it's 3. Now same thing I can do for 3, I get 2. Okay, so that is 5. And for 4, I can come to 3 and then go back twice. So that will give me 1 for 6. I'm coming from edges. Okay, I mean so 1 step going and then coming back. Okay, those are the 6. What are you? I'm not using like 2 step going. I'm just 1 step. So I will from 1 to 2 and then 2 to 1 and again 2 and then 1. That is 1. The same I do for 4 also. So those are 2. Now for 2, but it's 2, I can go to 1, come back, and then go to 1, come back. That will be 1. Okay. I can also do like from 2, I go to 3, okay, and then come back, and then again go and come back. That will be 1. I can go from 2 to 1 and come back, and then I can go from 2 to 3 and then come back. That will be 1. I can use like 2 to 3 first, come back, and 2 to 1. That I am using that 1. How many here? So from 1
ಇದು ಯಾವ್ದು?
ಅದು ಕ್ಯಾಮ್ರಾ ಸಾಸ್
ಇದು ಬೇಕಲ್ಲ, ಎರಡು ಸಾಸ್.
ಎರಡು ಫ್ಲೋ ಮಾಡಿದ್ದೇವೆ. ಯಾವ್ದೋ ಒಂದ್ ಸೆಷನ್ ಇದು ಸೌಂಡ್ ಇರಲಿಲ್ಲ, ಮತ್ತೊಂದ್ ಸೆಷನ್ ಎಂತ ಇಲ್ಲ ಅಂದ್ರೆ ಮಧ್ಯದಲ್ಲಿ ಇಂಟರ್ ಕನೆಕ್ಷನ್ ತಪ್ಪಿ ಹೋಯ್ತು. ನಾ ಮೇಲ್ಗಡೆ ಕೆಲಸ ಮಾಡ್ತಿದ್ದೆ, ಯಾರು ಕಂಡವ್ರು ಹೇಳಲು ಇಲ್ಲ, ಎಂತದು ಮಾಡಲಿಲ್ಲ. ಸೊ ಆದ್ರೆ ವಿಡಿಯೋ ಕ್ಯಾಮ್ರಾ ರೆಕಾರ್ಡ್ ಆಗಿದೆ, ಸೊ ಅದನ್ನ ಅಪ್ಲೋಡ್ ಮಾಡ್ಬೇಕು, ಅದು ಎಡಿಟ್ ಮಾಡಿ.
ಇದು ಯಾವ್ದು?
ಎಂತ ಮಾಡಿದ್ವಿ
ಆಫ್ ಅದು ಆ ಕಡೆ. ಮೊಬೈಲ್ ಗೊತ್ತಾಗಿಲ್ಲ. ಅಂತೂ ಈ ಕಡೆ ನಿಂತ್ರೆ ಕಾಣ್ಬೇಕಷ್ಟೇ. ಸಾಕು ಸಾಕು ಸಾಕು.
ಮೊಬೈಲ್ ಅಲ್ಲಿ ಲ್ಯಾಪ್ಟಾಪ್ ಅಲ್ಲಿ ನೋಡಿ ಅಂತ ಹೇಳಿ ಅಷ್ಟೇ. ಇದ್ರದ್ದು ಬಂತು ಕನೆಕ್ಟ್ ಆಗಿದೆಯಲ್ಲ.